When you're in the inner solar system, solar power is great. It's all you need. You just take photons from the sun, you convert them into electricity, and you can run all of your spacecraft systems. Even use it with an electric propulsion system to be able to fly through space. But once you get out beyond the orbit of Jupiter, once you want to go out to Saturn, to Uranus, to Neptune, to Pluto, to the solar gravitational lens, to access another star system, you need a longer-lived power system. And traditionally, space scientists choose an RTG, a radioisotope thermoelectric generator. This is a rock in a box, a chunk of plutonium or some other isotope that is producing heat, then use a thermocouple to extract electricity from the heat difference, and that powers your spacecraft. And it is very long lasting. The Voyagers have used an RTG for 50 years, and we're still getting data from them. So this technology works. But plutonium that is in the Voyagers is only one isotope. But in fact, there are a range of isotopes that a mission planner could use depending on what is the specific profile of the mission. Do you want high power for a short period? Do you want low power for a long period? There's a lot of options. So my guest today is Tyler Bernstein. He is the co-founder and CEO of Xeno Power. And Xeno Power has received a NASA Tipping Point grant to explore alternative kinds of RTGs for their various space missions. And so in my interview with Tyler, we talk about the landscape of RTGs and what kinds of different missions they could enable, including some science fiction-y ones, as well as the work from Xeno Power on integrating a Stirling engine, which can give you a higher power output for the same amount of heat. So if you want to learn more about RTGs, enjoy this conversation with Tyler Bernstein. Tyler, I've got a very technical audience. They know what a lot of the sort of spacecraft hardware is, but we're going to spend a big chunk of this episode talking about RTGs. And so can you just give people a great explanation of what an RTG is?
Yep. I'll start with the simple answer, which RTGs are hot rocks in a box. And in the middle, we have radioisotopes, hot rocks that are naturally and passively decaying over half-lives. And if you pick an isotope with a long half-life, that means for decades at a time, you're getting relatively constant thermal energy. You can then convert this heat into electricity, traditionally, as you mentioned, through thermoelectric generators, which use the Seebeck effect and the difference in temperature of the hot interior and the ambient environment. That difference in temperature, you get a current, you get electricity. So constant thermal energy, passively thermoelectrics converting this heat into electricity. And the result are small boxes, let's say roughly the size of a microwave oven, that generates reliable heat and electricity for years at a time that can be used anywhere on or off Earth. Doesn't need sunlight, doesn't need recharging, doesn't need refueling. This great foundation for energy in frontier environments, from the surface of the moon to deep space and in other regions as well.
When were RTGs first deployed in space?
Yeah, so the late 50s is when you started to see a lot of development here. In the early 60s is when you saw the first deployment of radioisotope power systems, or RTGs. So originally powering satellites. This was joint programs with NASA and the Department of Defense. So you started to see them in the 60s, and then where you really started to see them in, I would say, the most exciting way was in the Apollo program. And every Apollo mission actually had a radioisotope power system on board that was left behind on the lunar surface to power scientific equipment. So it's called the ALSEP program. This is where you started to see some of the real first deployments of RTGs to enable terrific science exploration in space.
Right. And then, I think one that people are most familiar with is what's happening with the Voyagers. They are 50 years after they launched, and they are still sending science data home thanks to these rocks in a box.
That's exactly right. And the Voyager spacecrafts and really all of the RTGs that have been built before for NASA and for the Department of Defense and space operations have used plutonium-238. And plutonium is an amazing isotope. It's an alpha emitter, so it's easy to shield. So you can build a lightweight system. It has a half-life of nearly 87 years, so you can have almost 2 decades of reliable electricity. And as you've seen with Voyager spacecrafts, even beyond those 2 decades, which is a requirement of these systems. And it's really incredible that 50 years later, we're still getting science back from these spacecrafts that have now left our solar system.
And that's the same isotope that we're seeing on Perseverance, Curiosity, New Horizons. If you're going to have something go away from the sun now, this is what you use.
That's exactly right. You see a really rich history. There's been, I believe, over 45 RTGs that have been launched into space that have, pretty much all used plutonium-238. It is kind of the pinnacle of isotopes, the Ferrari that you can use for these missions. The challenge is it's a relatively scarce and expensive isotope. So it has to be specially produced in reactors. Multiple Department of Energy national laboratories are a part of building our plutonium supply chain. Over the past decade, we actually ramped up our supply of plutonium-238, but that still results in only getting about 500 grams of plutonium every year. So right now, all of the plutonium that we're producing every year is being reserved for the Dragonfly mission to Titan in 2028, which, again, it's incredible that we're going to be able to have a nuclear-powered quadcopter traversing through the atmosphere of Titan. But what we're starting to see today is growing demand for a lot more missions that need radioisotope power systems, and the plutonium supply just can't support those.
Right. Okay. So I think that sort of gives people a pretty good understanding. So now, plutonium-238 is just one of these isotopes, but there are plenty of other isotopes that have different kinds of profiles. So give us a sense of what the actual landscape is for isotopes.
Yeah. So when looking at an isotope for a radioisotope power system, there's a couple characteristics you need to consider. The first is the half-life. You need something that has a long enough half-life so that you have relatively constant thermal energy for a long time so that you can have a power system that operates for a long time. That's the primary reason why in space exploration you want these, is because you can have sun-independent power for really long time periods. So half-life is really important. Another really important characteristic is what is the type of radioactive decay that you get. It's an alpha emitter, a beta emitter, a gamma emitter. And that has very different characteristics to how you shield these materials. So alpha, you only really need a piece of paper to block that radiation. Betas, you need aluminum foil. Gammas, you need concrete or lead. And if you're stuck with X-rays and you need concrete and lead, this means that you're going to have a really heavy system. And as we know, mass is very important in space. So for example, another isotope that's been broadly used before for terrestrial applications was a material called strontium-90. And unlike plutonium, which is, again, a relatively scarce material, strontium-90 is a really abundant material. There's been over 1,000 strontium-90 radioisotope power systems built before. The challenge with strontium-90 is that it's a beta emitter. So again, electrons are coming off. But because of a phenomenon called Bremsstrahlung radiation, which is when electrons get stopped in dense material and convert into X-rays, old strontium-90 systems had a lot of X-rays coming off. So they needed concrete and lead, and they were remarkably heavy, specific powers of, say, 0.01 watts per kilogram, which means they could really only be used on Earth. So they were used to power maritime buoys, Arctic sensors, but historically this isotope wasn't able to be used in space because it required a lot of shielding and was really heavy.
So that's one, which is one that's in sort of common use. But when you sort of think about if you sort of think about all of the isotopes that are available to you, how do things change?
Yeah, so again, apologies to kind of finish the thought there. So you have half-life, that's really important. How the shielding is going to be, how much shielding is going to be needed, that's important. The third characteristic really is availability of the isotope. There are a lot of isotopes in the world, a lot that if you look at those first two characteristics has a long half-life, is an alpha emitter that's easy to shield, but it doesn't exist in the world or needs to be specially produced in reactors. And that was really kind of the characteristic, frankly, that we looked at most when we sounded Xeno. We saw that there is a growing need for power from the seabed to the Arctic to the surface of the moon and beyond, largely market trends in the wake of a new great power competition. And if we were going to build a company that built dozens, hundreds, thousands of these power systems to meet this demand, that was actually the characteristic that we had to leverage the most. Curium-244 is a really interesting isotope. Americium-241, one that we're starting to pursue, is really interesting. But again, those supply chains don't exist. And that is really what drove us to strontium-90 when we started the company, was we wanted to start with an isotope that was broadly available so we could scale production and really build a company off of it.
So then let's imagine, you're talking about, strontium-90, you're thinking was it americium?
Americium-241?
Yeah, americium. So I would love to sort of just get a sense then of like strontium, you talk about those three factors. Americium, talk about those three factors. Like, I'd be interested to see sort of what are, I think most people now, if they imagine going to the RTG shelf, the RTG store, the only thing they can buy is plutonium-238. So let's imagine there's a fully stocked store where you could compare and contrast the different kinds of features. What would I be looking for as I consider my applications?
Yeah, let's go one by one there, right? So you have plutonium-238. Let's go through those characteristics. And a fourth one that we could add is specific power. And specific power and half-life are tied, but it's basically how much energy you're getting per gram of material. Plutonium-238, great half-life, 87 years. Alpha emitter, easy to shield. It is not very available, but we are producing it today just at low quantities, and it has a pretty good specific power. So you can build a high-dense trade system. So, that is really kind of the pinnacle of RTGs today, the Ferrari, if you will.
Right. I mean, when I think about the Voyagers, they were originally getting like what, a couple hundred watts?
100 watts, exactly. Yeah.
Yeah. And now they're down to whatever is a fraction of that, half of that. And so when you sort of think about that, when you're thinking about the sort of watts per gram,
Yep.
you're also factoring in the shielding.
Absolutely. And that, it's a great point there. And a lot of people, when they start looking at it, are just looking at the specific power of the isotope. But that's really incomplete, because you could have an isotope with a really great specific power, but it's giving off hard gamma, so you need concrete and lead. So yes, you can get really high density sources, but unless you're okay taking massive amounts of dose, it ultimately is going to be a really heavy system. So again, all of these kind of tie together. And the short answer is a lot of things look great on paper, and then you actually start digging in and you get to practicality, and there's challenges. And, no isotope is perfect. You take, the pros and cons with all of these. And again, plutonium is a great one because it does check a lot of those boxes. But there's other isotopes. Let's talk about cobalt-60, for example. Cobalt-60 is an isotope, really high specific power, shorter half-life, but you need a lot of concrete and lead. So you ultimately have this really heavy system, even though the isotope itself has a great specific power.
I mean, I'm assuming like if you're in space, like if you don't have people nearby and you're in space, you could theoretically configure your spacecraft so that the gamma rays are being sent off in directions you don't really care about. And what you do care about is shielded in a way that keeps it protected.
Absolutely. And, that is really shielding electronics, but you can be shooting the dose out into space. You have to deal with integration on the launch site. So how you're going to take something that is pretty dosey and actually integrated with the spacecraft. You also have to work through the launch approval process. There was a presidential memorandum in 2020, the 2019 that overhauled the launch approval process for spacecrafts with nuclear power systems. And it set down to tiers based off of the risk levels. And it's really a probabilistic risk assessment of what is the chance of dose to the public or the environment? How much dose would it be? So again, it's more complicated than just saying, let's take this really dosey thing, just protect the electronics and throw it into space. But to your point, there are some novel ways to navigate that. And you'll even see, if you look at the Voyager spacecrafts, they have these radioisotope power systems out on a buoy. They keep it pretty far away from the spacecraft, because even though plutonium-238 is an alpha emitter, it does have some spontaneous fission, so you get some neutrons. It's still good to keep it away so that you can reduce the dose of these spacecrafts, especially if you're going to be out there for decades.
Right. Okay. All right. So back to the store then.
Sorry, back to what?
Back to the store. Back to the isotope store.
Yes, back to the store. So let's bring in strontium-90. Strontium-90, half-life of roughly 30 years. It's a beta emitter, but because of Bernstein, you get some X-rays. It has a pretty good specific power, and the best part is it's really available. Strontium-90 is a waste product from the nuclear fuel cycle, and 5 to 6% of fissions in reactors result in strontium-90. And largely in the 20th century, a lot of strontium-90 was removed from what we call nuclear waste in the United States, largely up at the Hanford site in central Washington. So there's a lot of strontium-90 sitting around the United States, around the world, separated, decaying away every day as a liability to the taxpayer and the Department of Energy. And again, that was really the fact that made us say, that material's there. There are downsides. It today needs more shielding. We had some novel insights on how we could potentially reduce the bremsstrahlung and therefore reduce the need for shielding. But ultimately, the biggest advantage of strontium was it's available. Let's keep going into americium-241. Americium-241 is also an alpha emitter, so you get a lot of the benefits of plutonium and the fact that you don't need massive amounts of shielding. It has an over 400-year half-life, so it is a really, really long-lived system. However, that does mean that the specific power of the isotope itself is a little lower. Americium-241, not as available today. However, there are a lot of opportunities domestically and internationally to invest in and build up that supply chain, and ultimately have that supply chain surpass the plutonium supply chain. So that is actually where we have a contract with NASA, partnering with Intuitive Machines, Blue Origin, some international and domestic partners, to build a power system around americium and also begin to invest in that supply chain. So we see that as a really exciting isotope that kind of sits between strontium-90 and plutonium. And to kind of use a car analogy, if plutonium's your Ferrari, strontium-90 is Toyota Camry, maybe we're sitting with a Porsche or something with americium, where it's not as high performing as plutonium, but it's more available and more high performing compared to strontium.
And I know, I mean, there are other uses of plutonium, for example, with ICBMs and things like that. And so, do you get this sort of like separate non-military supply chain with the americium?
Yeah, so I think a key distinction with plutonium-238 is that that is a separate isotope than plutonium that is used in the weapons complex. Plutonium-238 is a very specific isotope that is primarily used for radioisotope power systems. Having said that, because it is plutonium, it's considered special nuclear material. So that does come with some more higher regulations around it, especially compared to strontium, that is just considered what's called byproduct material. So because of its ties to plutonium, which can be used for weapons, there are complications around plutonium-238, but that is a different material. Yeah.
All right. So I mean, is there anything else at the store?
Yeah, there's europium, there's curium, there's cobalt, there's a lot of isotopes that we like to call unobtainium. That yes, they look great half-life, great specs, great specific power, but they just don't exist. And building up radioisotope supply chains is challenging. And there's a couple ways you can get radioisotopes. One is you can get it from nuclear waste, use nuclear fuel, spent nuclear fuel as uranium fissions. You get radioisotopes. You can separate these radioisotopes from the rest of the waste, and have isotopes for use. And again, this is where we are getting our strontium-90. It is from separation from nuclear waste. France currently reprocesses nuclear waste. In the United States, there's a lot of efforts right now to renew spent nuclear fuel processing. There's one of President Trump's executive orders a couple weeks ago was specifically on this. So as we look at reprocessing in the U.S., as you look at it happening internationally, that is the source of isotopes. Another one is producing these in reactors. So this is where you put in a stable isotope, you bombard it with neutrons, and that turns it into a radioisotope. So you can put in, for example, this is how cobalt-60 is produced. Cobalt-60 is an isotope that is used right now to sterilize a lot of medical equipment. So there's a pretty big supply chain of cobalt-60, mostly built in Canada, actually, in Canada reactors. But that's another way to build it, is by putting stable isotopes in reactors, bombarding it with neutrons, and producing isotopes. That is a bit more challenging to stand up those supply chains. So that's where there's a lot of exciting opportunities at producing isotopes in reactors, but again, a bit more challenging than separating it from the waste. So again, the biggest challenge with these isotopes is how you get them. And again, that kind of makes a differentiation of an isotope that we can build a company off of versus an unobtainium isotope that looks really exciting, but is going to take billions of dollars of investments to actually get that supply chain there.
Right. But I want to talk about the unobtainium then. You've got me intrigued. So what would be the coolest isotope? The one that checks off as many of the boxes, I guess, delivers a lot of power, lasts for a long time, doesn't require a lot of shielding. Is there one that you're just like, man, I wish we had a supply chain for this?
Yeah, I mean, the first one that probably comes to mind is curium-244. Curium-244 is an 18-year half-life, so it's long enough that you can do a lot of exciting stuff, but short enough that you have a really high specific power. It's relatively easy to shield. That would be a really exciting, terrific isotope. Again, that supply chain just doesn't really exist today.
Right. So if you wanted to send a mission and deliver like 1,000 watts instead of 100 watts,
exactly,
for 18 years, that would be, or I guess it would be 18 years, but you get,
handful of years.
Yeah, exactly. That's really interesting. And so then, like, if we did want to create a supply chain, would it be? I'm guessing sifting through nuclear waste isn't going to get you enough of that stuff. Would you need a special reactor where you're just bombarding stuff to try and bring them up to that level?
Yeah, and I knew this at one point. I don't know it exactly, but curium has to be specially produced in reactors, and it's a multi-step process. I think you start with plutonium, you get to kind of a multi-step process where you produce an isotope, it decays to another isotope, you then bombard with more neutrons, and something for the viewers to look up, probably a good ChatGPT question of how you produce curium-244. But it's an extremely intensive process that, again, would take a lot of money to scale that up. And even if you could scale it up, the amount that you could produce is probably not enough to really be sustainable for certainly a business and, even for a government to probably make that investment.
Right. Okay. So I think we've got a good idea of what are the different isotopes that we have to work with. So I want to talk about missions then. So if we want to, when you think about things like the Voyagers, or I'm trying to think like something that would maybe go out into interstellar space, something that would operate out at the solar gravitational lens, where you're going to probably need about a 20-year cruise time just to get into position. what are some missions that you've been thinking about that would work with different kinds of isotopes?
I'll start off with the fact that solar power works great for most things in space. Certainly if you're orbiting the Earth, as you stay kind of within Jupiter is generally the range when solar power works really well. But there are some places where solar doesn't work well. The lunar night, when you're on the moon, you're generally in lightness for 14 days and darkness for 14 days by the way the moon orbits the Earth and Earth orbits the sun. In those 14 days of darkness, it drops below 200 degrees. If you have solar power and batteries, you freeze. There are permanently shadowed regions on the south pole of the moon where these are craters that we hope and think have ice, which can be used to obviously create water or rocket fuel. It's hard to operate in those shadows only with solar power. As you go away from the sun, solar radiance decreases by a square of the distance. So solar radiance drops relatively quickly. So once you get really beyond Jupiter, the amount of solar panels you need to power a spacecraft would just be incredibly massive that it makes it nearly impossible to operate. And on a lot of surfaces, whether it is the surface of Mars, where you have a lot of dust to make solar challenging, or the atmospheres of Venus, where a lot of the extreme environment makes it challenging. There are a lot of interesting places in our solar system where we want to explore and solar power doesn't work. And that is really where radioisotopes come into place. Places where, yes, you have that long cruise, you need really long-lived power. You want to go beyond Jupiter and into deep space. You want to survive the lunar night, to operate in permanently shadowed regions, explore the surface of Mars or the atmospheres of Venus. Again, these are great places where solar power doesn't work, and you have a really strong need for the reliable, always-on energy from radioisotopes.
But I really want to think about different isotopes for missions. Like when would I use americium? When can I, what kind of a mission could enough americium give you to be able to do something that's kind of novel and interesting?
Yeah, so we see americium supplementing the plutonium missions. The characteristics we expect to get from that power system are going to be not quite as good as plutonium system, but relatively comparable. And with that, we see a really exciting opportunity to really unlock science missions that simply can't happen today. If you look at the decadal survey, the decadal survey that NASA does to look at what science missions they want to fund, one of the biggest limitations is the amount of radioisotope power systems they have. We can build one, maybe two of these per decades, which means only the highest ranked missions get access to radioisotopes. But as we start to see in materials such as americium come online, and we can now build dozens of these per decade, that now allows a lot more science to happen because we can enable missions that today just couldn't happen because plutonium didn't exist. So that's where we see a play for americium is really supplementing a lot of space exploration, deep space missions where plutonium historically played. Now, strontium-90 has a bit of a different role that we see in space, and that is because it is going to be heavier. It needs more shielding. It's a bit of a clunkier system, but we see it being really valuable for a lot of lunar operations. So over the coming decade, depending on the studies you have, there are between 1 to 200 planned missions to the lunar surface. A lot of these being led by the government, a lot of them commercial. And when you're on the moon, if you want to operate for more than 14 days, radioisotopes are a really terrific way to survive and eventually operate during the lunar night. And we see strontium-90, a system that is a little heavier, playing a really great role there because it's going to be more affordable. So as you look at a lot of these missions that are in the, say, $50 to $100 million range, a strontium-90 system can fit in really nicely with the price of that. Yes, it's a little heavier, but we're looking at smaller systems to provide heat and small amounts of electricity to survive the night, operate during the night, operate in permanently shadowed regions. And we see a really exciting opportunity for strontium there, especially because the quantity of systems that we can build because of the availability of that isotope.
And what about cobalt? Do you see some uses for that in space?
Yeah. I personally think that the short half-life of cobalt will deliver 5 years, and the fact that it needs a massive amount of shielding makes it relatively difficult to close in space. I think some
Yeah.
people will disagree with that. I'll go on a kind of a quick tangent of another kind of exciting opportunity for radioisotopes, and this is more in the national security space, but is really focused on propulsion. So if you get a really high specific power isotope, you can get to maybe kilowatts of electricity in a really high density power source, and that can do some interesting thing in building highly maneuverable satellites. So that's kind of more of a national security play. That is where I think there could be some opportunities with these these really high specific power but lower half-life isotopes. But for a lot of the lunar surface space exploration, I think again, the short half-life and the fact that you need a lot of shielding makes cobalt challenging for those environments.
So I want to talk about then some possible missions that for example, like let's say we did want to go out to the solar gravitational lens.
Yep.
Right? We've got a cruise phase here of probably, 10 years if we're fast, probably more like 20 years. And then we want to start operating this telescope.
Yep.
What would you pick?
Americium-241. Half-life of over 400 years means that you are getting constant power for truly decades. Kind of the rule of thumb is that 10% of the half-life is like when you're going to be operating perfectly. You can probably double that, maybe triple that, and still be valuable. So if we look at strontium-90 with a half-life of 30 years, 3 years, great, maybe up to 10 is kind of where, and this depends on the specifics of the mission there. Plutonium-238, half-life of 87 years. They have really 17 to 18-year mission requirements. So again, we're looking at kind of 10 to 20% of that mission. But going beyond that, it starts to get challenging. Yes, Voyager is operating, but we're at relatively low amounts of power that's limiting the mission. Americium, half-life of 400 years. We're looking at 40, 50, 80, 100 years of really constant power. So for missions like that, where you need truly decades of constant power, Americium's a really terrific pick.
Yeah. And like same thing, you want to send a probe to another star.
Yep.
That's what you choose.
Exactly. Now let's counter it. If you're on the lunar surface and you want 1 to 2 years of operations, again, that half-life of strontium-90 is really great. Then there's no need to use americium, which is going to be more limited supply than strontium for some of those missions. Let's reserve americium for these really exciting missions that need it. It's also going to be a more expensive isotope. So again, it's, kind of balancing cost with performance, with half-life, all kind of, having different mission specs for that.
Yeah, and I can imagine if we end up with more infrastructure on the moon, maybe we have fission reactors on the moon, they're producing nuclear waste, we're then processing the waste on the moon to use to build RTGs.
In situ, radioisotope power system development on the moon. Exactly.
Yeah, exactly. Okay, very cool. And is there anything like that would last for like a long time? Like, let's say I wanted to have a probe last for 10,000 years. Is there any isotopes out there that would allow me to do something like that? But only give me like, a watt, right? But it wouldn't have to be a very interesting thing, but maybe it would just continue to communicate.
That is a great question. I will have to maybe take a rain check on that one.
Sure. Yeah, we'll ditch that from the interview then.
Yeah, I mean, carbon-14 has a half-life. I think it's like 5,000 years. And there's been some development of carbon-14, like beta voltaic, really small systems, so you can get microwatts to milliwatts of electricity. So you stack those together, 5,000 years, are you going to get 10,000 years of power? Maybe not, but maybe we can get you a couple thousand years of power. So maybe we'll go with carbon-14 is an interesting one there.
And that's the same thing that's sort of helps us figure out the age of wood.
Exactly.
On Earth.
And again, the challenge is because that really long half-life, it's such a low specific power, so you can't get that much electricity. But again, the long half-life and very low power could have some niche uses for extremely long missions.
Yeah, that's really cool. All right. Now, I know that you are considering Stirling engines as a way to extract the energy out of RTGs. And you mentioned early on the traditional way is that, you're using the heat and then you're using, you're just extracting the heat and turning that into electricity with a thermocouple. How would a Stirling engine do this differently?
Yeah, so with thermoelectrics, you have solid state system. You're just using the Seebeck effect to convert this heat into electricity. Stirling, we're now introducing moving pieces, and you have a piston moving in a gas. A difference in temperature compresses the gas, and that creates the piston to move. You get electricity. Stirling engines, of course, relatively proven technologies. However, there's some nuances when using them in space and using them in small scales. Stirling actually gets a bit more challenging as you're scaling down in size. So when we look at thermoelectrics, solid state, zero moving pieces, 5% efficiency of heat into electricity. Stirling engine, moving pieces, today lower technology readiness level. There has never been a radioisotope Stirling generator that's been built. However, you can get 20, 25, 30, potentially even higher percentage of that conversion of heat into electricity. And that does a couple things. One, that can increase the overall specific power. As we look at the watts per kilogram that you're producing, for the same amount of nuclear material, you're getting 5 to 6 times the amount of electricity. That's terrific. What's also really exciting about that increase in efficiency is you maybe just need less material to get the same amount of electricity. So when we're looking at isotopes that are scarce, plutonium, to an extent, americium, we can now make that same amount of material go a lot further. So a lot of advantages to Stirling. And, it's a reason why NASA has been investing in this for quite some time. They've invested couple $100 million into development of Stirling engines for radioisotope power systems. NASA Glenn has really taken the lead here and has been testing Stirling engines with an electrically heated source for quite some time. And we now have multiple programs with the Department of Defense and NASA where we're now maturing these radioisotope Stirling generators. Next year in 2026, we'll actually be demonstrating to what our knowledge will be the world's first radioisotope Stirling generator, actually coupling the radioisotope source with the Stirling engine. And in our program with NASA, we're also working to mature this for space environments, and that's in partnership with Blue Origin, with Intuitive Machines, with NASA Glenn, and other great partners.
That's really cool. And I know the Chinese, I reported on this, the Chinese have tested a Stirling engine on their space station.
Yep.
So are we going to see potentially an American-built Stirling engine tested in space?
Yeah, there's a couple really exciting programs going on right now. I won't call out specific names without their approvals, but companies that are looking at building and deploying Stirling engines in space. All of these will be electrically heated. So again, we're not actually going to be using a nuclear source to provide that heat, but still a great demonstration of this technology in the environment and de-risks that to then, great, in a couple of years, let's actually make this with a radioisotope source, launch it into space and have a higher specific power radioisotope power system, or just get a lot more bang for your buck with the isotope you're using.
Yeah, that's what I was thinking. Like, if we only have the amount of plutonium to get us 1 to 2 missions per decade,
it could now be 5 to 6 missions per decade.
5 to 10. Yeah, that's great. Yeah. Wow, that's really interesting. And there's like one of my favorite stories that I reported on. It feels like 15 years ago, people were looking at how you could use a Stirling engine on Venus, but run it in reverse.
Yeah.
Where you've got this sort of keep the interior of the spacecraft cool.
Yep, a nice cryo cooler.
Yeah. And then you're slowly letting the heat come in and derive power from that.
Yeah, that is there's a lot of fun concepts out there. I think I'll just add one of the challenges of Stirling engines, though, and part of the reason why they haven't really been used in a lot of space exploration is we're now introducing moving pieces. And things that operate for a really long time and moving pieces, that's inherently challenging. So, for example, if we are going to use a Stirling engine to power, let's just say, another Mars rover, that's a multi-billion-dollar program. And you're not going to rely on a moving piece that could break. And if it breaks, the spacecraft goes down. And obviously, there is no one on Mars to operate this. Let's go even further. The Voyager spacecrafts to really want to operate for decades. Do we want to assume that this moving piece can operate for decades at a time? So a lot of the testing going right now in NASA Glenn is to show the reliability, showing that it can operate for years at a time. I'd say where we're excited about Stirling is a lot of those shorter missions where we're, say, between 1 to 5 years, we have more confidence in the reliability. I think it's going to take some time to get confidence that these can operate for decades at a time and to actually use these in these very high profile, extremely expensive missions. Again, just given that need for ultimate, really high reliability for those missions.
Yeah. There's got to be some kind of really interesting sort of plans for this, but I can totally imagine when I think about how reaction wheels have broken, like that's the part of a spacecraft that breaks,
right?
Is this thing that's spinning at, thousands of RPM. It's a moving piece. It goes, the whole spacecraft goes. And so in this case, your Stirling engine goes, the whole spacecraft goes. So,
and I'll go again, vibration is a big thing with spacecrafts. And if you have only one piston that is moving, that is going to be vibrating the spacecraft, which is, not great for a lot of equipment that you have. So you need to either balance that out or have two Stirlings that are operating to balance each other out. So there's more complexities as well as you add moving pieces just to ensure that the payloads you have, aren't being impacted by that.
Right. But that 5 times power sure feels like a good reason to investigate. Tyler, what are you obsessed with right now?
What am I obsessed with right now? I think in the last really month or two, it's been the lunar economy. As we look at going back to the moon right now, there are really 2 primary reasons and tailwinds for going to the moon, or reasons why we'd stay on the moon. One is really there's 3 reasons: national security, science, and commercial endeavors. National security is, right now, there is one country that's operating 24/7, 365 on the moon. That is China with their Chang'e 4 lander that is powered by plutonium. Meanwhile, over the past couple months, Intuitive Machines and Firefly landed on the moon, and they died after a couple days because they froze to death during the lunar night. So from a national security standpoint, the moon is the ultimate high ground. Right now, China is operating there. They're planning to have bases. The United States does have a national security imperative to go back to the moon and operate in the cislunar environment. So that is one thrust. The second thrust going back to the moon is science. There's a lot of amazing science that we can find on the moon, deep understandings of why we're here, of our solar system. And of course, that is one of the primary thrusts of NASA, is to go for scientific purposes. The third thrust is commercial activity. Is there money to be made on the moon? Can we mine and get helium-3? Can space tourism be enough of an industry that can sustain operations on the lunar surface? What are other materials that we can get in that region that can be brought back to Earth and making money? And if we want to actually have a sustained presence on the lunar surface, we need those tailwinds. The first two, however, are really dependent on time and politics and geocompetition. And as we saw after the first space race in the 1960s, again, the thrusts there were really national security, to an extent science. We got to the moon, the Soviets didn't, and that was the end of it. And that meant that for decades, we stopped going to the moon and we stopped going deeper into space. And right now, we're fortunate that those tailwinds are there. There are national security, scientific tailwinds going back to the moon. But my concern is that, is that going to be the case 5, 10, 15 years from now? The one thing that can endure political turbulence is the opportunity to make money. We are in a capitalist society, a capitalistic world. And if this time going back to the moon, we can find a reason to stay there so people can make money, that can really sustain this long-term presence, and meaning that we will go to the moon and never leave. And there's a lot of amazing companies, Interloon, Rob Myerson, former CEO of Blue Origin, is looking at resources on the lunar surface. There's other companies that are looking at putting data centers on the surface of the moon. Other companies looking at what we can make in low gravity environments there. Again, of course, tourism. So we've been spending a lot of time, talking with our team, a lot of people in the industry, of what are going to be these hooks that can be this foundation of the lunar economy that can endure past potential political turbulence or tailwinds or shifts in, what the United States government decides to do. And that, of course, I know we said we weren't really going to talk about it, but something that is even more paramount as we look at some of the NASA budget cuts and what the United States ambitions are in the moon and beyond. So I'd say, what am I obsessed with right now? It is finding an economic purpose to go to the moon and stay on the moon so that we can go there and never leave, as we did, different
Right.
than what happened
Yeah.
in the 1960s.
Yeah, I think about this a lot. And, I've interviewed a lot of people and many different companies that are sort of in this same thing. And I think I'm very skeptical that anybody has a really clear pathway to anything that is a feasible economic case for doing anything on the moon today. There's a lot of really interesting things, as you said, about like in situ resource utilization and so on, but those would support existing infrastructure on the moon. So if you do want to build up a base, then and do science, then if you can develop some in situ stuff, and you can imagine there being economic reasons to send resupplies and send more scientific instruments and all that kind of stuff. So, as long as the scientific incentive is there, I can see a lot of investment into sending stuff there. But for someone who just wants to go to the moon and make a buck, I think it's still going to be a long way. And I 100% agree with you. Like, to have, it's sort of like what we do with Antarctica. Antarctica is this place where people go and they do science. They go to Concordia Station and they're fully supported by the governments that are part of this consortium. And I think the moon is going to be like that for quite a while, and even our future. And yet you can sort of imagine this future. If we just continue increasing our gross domestic product of humanity, there will be this time when we are a fully space solar system exploring civilization, and these economic things have been figured out. But, I've just reported on so many asteroid mining companies that have gone out of business, and that, I sort of feel like it's going to be a long time before we can find it. But if you can figure it out, I can't wait.
I'll give you two examples that I think are exciting. And I would agree with you to an extent that there is, it's the definition of a moonshot to actually try to make money on the moon. And I'd say from a Xeno standpoint, that's why we're really excited that we have our terrestrial markets that we're also pursuing, maritime, Arctic, and elsewhere, that kind of provides this base of the company so that hopefully if and when the lunar economy develops, we can play a big role there. But I think two examples are, one, mining helium-3 on the moon. And, you kind of mentioned in situ resource utilization to support operations on the lunar surface, helium-3 is a really scarce isotope on Earth. It is really valuable for quantum computing and eventual fusion reactors, and a lot of it on the moon. So I think that's an example of a material that is more available on the moon than on Earth. And if we can actually get to the moon in an economic way, bring that helium-3 back, I think that's an example of something that's actually supporting operations on Earth. But there's a lot of work to get to that point.
Like
Another
learning how
one.
to fuse, like how to do fusion at all.
What do you say?
Well, we don't even know how to do fusion at all yet.
that is correct.
Right.
And quantum
So I sort
computing
of
is
think of
nascent as well. So it's kind of, stacking challenges on challenges. But, I think that's one example. Another one that I think is fun, and I will be honest, say that I don't know this in great detail. But, again, if there's a lot of ice on the moon, you can break apart ice. You can create rocket fuel from that by getting hydrogen. And because of how difficult it is to get off Earth with the gravity of the Earth versus how relatively easy it is to get off the moon because of the low gravity of the moon, if we could actually create rocket fuel on the moon, that could be really valuable in refueling satellites, especially in GEO. So as we look at potentially more mobility on orbit, and we look at refueling, it could be way easier and more efficient to actually refuel from resources on the moon than bringing resources from Earth into space. I think it's kind of another example where you have to, think about what the future could be. A lot of things have to happen, but, potential opportunity to make money on the moon as well.
Yeah, that's really interesting, and I think you're right on that one. I'm a little more skeptical on the helium-3 side of things, but I think you're right that if we it's about the miniaturization, it's about the technology constantly improving, better reusable rocketry. Like as we get better at flying in space, then suddenly someone's going to go, hey, I can just drop a rover down at the lunar South Pole. I can collect enough material. I can then launch from the surface, visit a spacecraft that's almost out of propellant, deliver it a fresh batch of propellant, and that cost is cheaper than them launching with a larger propellant store or them trying to send up a mission from Earth. And once, just it's gas stations, right? Like obviously gas stations work on Earth. And so they could theoretically work in space if we can get the propellant from the moon cheaper than we can get them from Earth.
It's exactly right.
Yeah.
But, to kind of summarize all of this here, I do think if you look at the United States ambitions with NASA, with the Space Force increasingly talking about cislunar and the lunar environment, if you look at China's ambitions in the coming decades to set up a base on the lunar surface and one that will not just operate for a little bit of time, but have a sustained presence, I do think that there are tailwinds for the next couple decades from the science national security standpoint to take us back to the moon. And I think the question is then, during these couple of decades where you have the government supporting this, will we find that economic hook that will be the centuries-long sustained reason to be on the lunar surface and beyond? And obviously, there's a lot of opportunities beyond in asteroid mining and going to Mars and whatnot. And the moon is also a great base to going to Mars. So there's a lot of hooks that could be it. But again, to kind of go back to your question, what am I obsessed with is what is that hook that really makes going and staying on the moon sustainable and not reliant on government support or lack of support.
Yeah. Well, fascinating conversation. Tyler, thank you so much for your time.
Yeah, thank you, Fraser. Appreciate it.
I hope you enjoyed that conversation with Tyler Bernstein and have learned a lot about RTGs. Now, we had a longer conversation where we talked more about the difference between exploring space and the oceans and how RTGs can work in both of those and how they're similar and how they're different, as well as some of the environmental concerns. So if you want to check that out, that's over on Patreon. It's completely free. There's no ads. We'll just put a link down. We call that Interview Plus. So check that out. There'll be a link in the show notes. You can watch that version of the interview. Now I'm going to give you some final thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Gilton, and David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Moore, Jay Graves, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Roebuck, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler-Melly, Thomas Ilskadron, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. All right, well, that was a really useful interview for me. I understand RTGs. I thought I did, but it sort of dawned on me after doing some reporting that there were these different flavors, different kinds of isotopes. And it was great to have this conversation with Tyler to kind of boil them down into, the isotope store and what they're all good for. And I think this is going to be really interesting in the future, that we can see many more missions with different kinds of isotopes fulfilling different purposes for us to be able to explore deep space and get a lot more missions off the ground, literally. Now I'll put some links to some other interviews that I've done right here, but I hope you enjoyed it, and we'll see you next time.